Welcome to Etch Processes for Microsystems Fabrication Part 1, presented by SCME, or the Southwest Center for Microsystems Education. In previous presentations, we have discussed the deposition and photolithography processes. Both of these processes usually precede an etch process. In deposition, a thin film layer is deposited on the surface of the wafer, and the purpose of this film can be structural, sacrificial, as an insulator, a conductor, a protective layer, or in the case of photolithography, a photosensitive layer. In photolithography, the photosensitive layer or material, which is normally called resist, is deposited on top of another thin film. The resist is then exposed and developed, leaving a pattern that will be etched into the thin film layer or underlying layer. For microsystems fabrication, etch is a process that removes select materials from the wafer surface, below the wafer surface, or from within the substrate. In this graphic, we can see all three. Surface etching created the sensing elements and on-chip circuitry on the surface of the wafer. Bulk etching created the opening underneath the sensing element in the bottom figure, as well as the back-etched cavity in the top figure. Using different types of etching processes allows flexibility in the construction of micro-sized devices, as well as the construction or fabrication of the supporting electronic circuitry. The construction of a microsystem may consist of several different devices and layers. Material is deposited and removed several times during the fabrication process. As previously mentioned, it may be desirable to remove material at the wafer surface, below the surface, or within the substrate, all of which require different types of etch processes. The type of etch process that is used depends upon what type of layer is being etched. Here we see several micro devices that are made possible due to the etch processes that have been developed for microsystems technology. Many of these processes were originally developed for integrated circuits and are being used in microsystems today. However, some unique processes have been developed to create objects such as the neuroprobe seen here in the scanning electron microscope image. The tips of these probes are less than 10 nanometers in diameter, while the length of the probes are between 1 and 100 micrometers. This microgear and alignment pen use several different types of etch processes to create the shapes seen here, as well as to allow the gears to rotate freely above the substrate surface. These optical mirrors found in digital projection systems are etched so that the hinges underneath the mirrors tilt the mirrors in different directions at a rate of 30,000 cycles per second. All of these devices are only possible using etch processes. So let's take a look at some of these different etch processes. As I stated earlier, microsystems fabrication utilizes many different types of layers to create different types of components. Some layers allow us to incorporate transducers into a MEMS device by using, for example, this cantilever sensor, which has a silicon nitride structural layer and a gold layer that actually has two purposes. The gold layer is chemically inert to the target molecules being analyzed, and its resistance changes as the cantilever bends or flexes due to the heat generated in the chemical reaction on its surface. The surface layer is a chemical reactive layer that is chosen for its selectivity or its ability to recognize and capture specific molecules. Such sensors are used to identify specific gases such as ammonia. In fact, one such sensor is currently being used on the International Space Station to detect ammonia leaks. When building the electronics for a microsystem and for outlining mechanical components, the goal of the surface etch process is the same as that for building integrated circuits. Remove selected regions on one layer, a surface layer, of the wafer to create either a structural pattern or to expose an underlying layer of a different material. For integrated circuits, the underlying layer is the conductive interconnect. Connections between different conductive layers can be completed. For mechanical components, the surface layer is patterned with specific shapes for structural components such as cantilevers, mirrors, or probes. These mechanical elements can be conductive, as in the case of electrodes or cantilevers. The exposed underlying layer can also allow one to anchor a mechanical structure to it. For example, these gears and alignment pin were fabricated using the Summit 5 process developed at Sandia National Laboratories. The gears and pin were all fabricated on the surface of a wafer. You can see different layers in the scanning electron microscope image. One layer you don't see is the sacrificial layer, which is now the spaces between the gear and the substrate and the gear and the alignment pin. The alignment pin is anchored to the substrate in a different step of the process that was used to form the pin itself. Each of these layers required a deposition, photolithography, and an etch process. The bulk etch process is used to remove materials from underneath a layer or from the back side of a wafer. This graphic illustrates a movable mass that is etched from within the substrate. The mass is suspended over a layer at the bottom of the substrate by springs that have been surface etched from silicon nitride. This mass is part of an accelerometer. When the mass moves up and down due to movement, this movement is sensed by the electronics built into the device. This graphic shows the backside of a wafer that has been completely etched through the substrate to a layer of silicon nitride that was previously deposited on the front side of the wafer. The hole in the backside of the wafer is the reference chamber for a micropressure sensor. You can see the electronic sensing circuit on the front side of the wafer by looking through the etched hole. A combination of these processes, surface and bulk, allow for the construction of a variety of electronic and mechanical devices on the same microchip. So as you've seen, bulk etching is a process that removes select portions of a substrate or layer or removes the entire layer. Bulk etching is not unique just to microsystems. In fact, bulk etching is older than human existence. For example, in nature, bulk etching formed natural bridges and arches as the natural arch seen here. These structures were formed with material underneath was etched or removed by wind, rain, water, and just natural erosion. Etching is accomplished through either a wet or dry technique. Wet etching removes the material through a chemical reaction between a liquid etchant and the layer to be etched. Wet etching usually takes place at a wet bench with proper exhaust because many of the etchants, the reactive chemicals used in wet etch, are very caustic and they emit vapors that must be controlled. Wet etch processes also require that acid gear be worn by anyone who works with or around the wet etch area. Dry etching removes the material through a chemical reaction or a physical interaction between etchant gases and the exposed layer. Dry etch processes require expensive, high-energy plasma systems, such as the one shown here. In a dry etch process, the plasma is struck, causing the molecules of the etchant gas to experience high-energy collisions, forming positive ions and free radicals. Each of these particles has a definitive purpose in the etch process, and we'll be discussing this in Part 2 of etch processes. In the previous slide, we talked about etchants. Just as different materials are selected for their functional properties in creating the various layers of MEMS, different chemicals are selected to etch these materials. Etchants are chemical compounds which chemically react selectively with the layer to be removed, thereby removing the layer. Some common etchants used in microsystems fabrication are potassium hydroxide, which is used to bulk etch silicon, hydrofluoric acid, which is used with other chemicals to etch silicon dioxide, and some metals such as titanium and tungsten, sulfuric hydrofluoride for silicon nitride, and boron trichloride for metals such as titanium and aluminum. In many wet etch processes, the etch is isotropic. An isotropic process is a chemical process that etches the selective layer in all directions. This image shows the silicon nitride layer being etched vertically as well as horizontally and diagonally. In other words, the etchant is etching any of the silicon nitride that it comes in contact with. But notice that it is not etching the masking layer. And once the silicon nitride is removed down to the substrate, the etchant will not etch the substrate. At this point, the etch could be complete and the wafer removed from the liquid etchant and rinsed to stop the etch. Because this etch does etch in all directions, you do get undercutting or removal of the silicon nitride from under the mask. In many cases, this is expected and acceptable. However, there are some cases where this is not acceptable, therefore another type of etch process, such as a dry etch process, would be required. In microsystems, the wet etch process is extremely handy in removing sacrificial layers, as we see here. Think about what would happen if the wafer were left in the liquid etchant, even after the substrate was reached. At this point, the etchant would continue to etch sideways underneath the masking layer and eventually remove the entire layer of silicon nitride without etching the mask or the substrate. This characteristic makes it very effective at removing a bulk of material such as a sacrificial layer or a masking layer. Wet etch is performed in an immersion tank containing the etchant solution. The wafers that are going to be etched are placed in a wafer carrier known as a boat, and this carrier is then lowered into the tank containing the heated etchant solution. The wafers are left in the solution for a calculated amount of time. Two critical parameters monitored during the wet etch are the concentration of the solution and its temperature. Both directly affect the etch rate. An increase in either parameter increases the etch rate. For example, a buffered oxide etch is a solution of hydrofluoric acid, or HF, and hydrogen peroxide. An increase in the ratio of HF to peroxide would increase the rate at which the oxide were etched. An increase in the temperature of this solution would also increase the etch rate. Once the etch time expires, the wafer carrier is lifted out of the tank and transferred to another tank where it is rinsed with ultra-clean deionized water. This graphic shows a quick dump rinse, or QDR, in its rinse cycle. A QDR sprays the boat with deionized water while simultaneously filling the tank. The water is then dumped and the cycle repeats for several more rinse-dump cycles. After the QDR, and before the wafers can be processed further, they must be thoroughly dried. The presence of water, even in minuscule amounts, will interfere with future processing. Typically, the wafers are placed in a spin rinse dryer, or SRD, where they are rinsed again and then dried. The SRD's operation is similar to a centrifuge. The wafer carrier is placed in the machine and rotated while being rinsed with deionized water. After the rinse, the water is turned off, and the carrier continues to spin but at a higher rotational speed. Heated nitrogen is then introduced during the spin, removing any remaining water on the wafer. Now that you know the basic wet etch processes, let's talk about specific types of wet etches. A specific type of wet etch process uses potassium hydroxide, or KOH, to etch crystalline silicon. This etch results in an anisotropic etch profile, or what is referred to as straight wall profile. The KOH etches the silicon along a specific crystal plane of the silicon. In this figure, notice the straightness of the angled edges of the bulk etch compared to the curved edges of the isotropic etch that you saw previously. This is due to the high selectivity of KOH, which is a liquid etchant, and the crystalline structure of the silicon. This same type of anisotropic wet etch is used to form the cavity underneath this perforated electrode shown here in this graphic. Another type of anisotropic etch is a vertical wall profile like the ones that you see in these two graphics. To achieve such profiles, a dry etch process is required. Be sure to view Etch Processes Part 2 to learn how these straight wall profiles are made, as well as how we can achieve the high aspect ratio seen here on this graphic, where we have an etch that is many times taller than it is wide. For more detailed information on these etch processes, be sure to download the Etch Overview Learning Module from the SCME website under Educational Materials. Part 2 of Etch Processes is available through YouTube and online at the SCME website. Thank you for viewing this presentation produced by the Southwest Center for Microsystems Fabrication.